Well, good morning. This is 9:35 on Monday morning, the 19th of September, 2016. Should be Math 126, and I'm the only person in the room, so that's not a good sign, but hopefully some of you will be showing up in a minute. So let's just get on with calculus. We're in Chapter 6, Section 6.2. Page 342, bottom of the page, example 3. We got this far last time, but weren't able to get this problem covered. It's a pretty simple one, so let's hit it. Well, my whole screen's gone blank, as I guess yours has too. I guess it's trying to find itself. Don't know why this would have been the case. Okay, here we go. We're still not there. This is what they call presenter mode, and everything's sort of reduced on that, so I'm going to hide presenter mode, but now it hit it too well, so I have to do a couple of clicks here, and we should be back. All right. So here's example 3. Compute the volume of a sphere of radius r. All right, now it could be that I haven't taken enough time to talk about how to set these things up. I think we got someone coming in now. All right, I don't have to talk to myself today. I was going to feel a little crazy. Marcus, right? Okay. So good to see you. I hate talking to myself. I feel like I may be losing it. All right, I was already getting started, but I don't turn on the projector until somebody else is in the room, so it's going to take a couple minutes to warm up. But I did want to say this, especially to you, De Silva and Theo, and you know, Theo told me he goes by Theo, but in my roll book, I just marked him as Theo. Okay, sorry. So, we had our first meeting for the math team last Friday. It didn't even last an hour, 1 to 2. We've got 6 people who are interested. Not all of them showed up, but most of them did. We'd really be great to have 8 people on so we can have 2 teams, because you can only have 4 people on a team. So really, we'd love for you to consider, any one or 2 or all 3 of you to consider whether you might want to be on this. I also see another huge advantage for y'all to do it. It will take some time, but guess what? You get to practice calculus outside of calculus class, and you get to learn some stuff you probably haven't gotten to yet, and review a lot of stuff that you have had. I can't see anything but an upside on this. I don't see any downside, except it will take a little bit of time. It's a fun group of people. The ones that were there last time, I think you'll find really are enjoyable. And what we're doing, I'm going to be meeting with the ones who can come to this campus. I believe we finally decided on Tuesday, Thursday afternoon. Let me see if I can remember the time. One student is available. No. Okay. One student's available anytime after 12:30. But the other one can't be here that early. So sometime later in the afternoon. I'm going to say maybe after 1 o'clock, but it may be a little bit later on Tuesday and Thursday, giving time for this one student to come from the Birmingham campus and come over here. I'm going to meet with 2 students then, and we're going to go through practice problems that they've had on previous competitions, but they won't have the same problems, but it'll be similar to it. And it is a fantastic review of calculus. I mean, a fantastic review of calculus. And then in some parts, it will also be a pretty good review of pre-calculus, which would be really old hat to you. So, and here's Theo. Sorry, I was just saying before, I had circled your whole name in here, but in the beginning of the term, you said you went by Theo, and I've been calling you Theo. So, sorry, Theo. Okay, good. And what I was telling Marcus before you came in, the math team did meet, first meeting, last Friday. Didn't take a full hour, but it was a good group of people. Let me hang off and get all three of you here. All right. Good deal. I don't know if Muhammad is going to show up. It looks like not. So let me start over with this then. The math team met for the first time Friday. Have a total of 6 people signed up. All 6 were there, but close to it. A couple came in late. I think we're only missing 1 person out of the 6, but they said they were interested. What we really need is at least 8. Now, we can't have more than 8, but we really would be great to have 8, because then we can field 2 teams. Okay? Now, what the others decided to do, and all the instructors who teach calculus were there, and in fact, all the instructors who teach pre-calculus and calculus, full-time instructors were there. And what we decided is we would meet with the students and go over the practice problem. Now, I didn't bring them up with me today, but I can get you copies of that if you're interested in doing it. And it is a fantastic review of Calculus 1 and also Calculus 2 and a little bit of Calculus 3, mostly of Calculus 1. I think like 60% of the questions are Cal 1 questions. But guess what? You run into that stuff again over and over again. So it is. And so the students who are here who want to come out here to practice, I'm going to meet with them sometime Tuesday, Thursday afternoon. I don't remember. One student's coming from the Birmingham campus, so he gets here at either 1 o'clock, 2 o'clock, something like that. It might be as late as 3, but it seems like it. Yeah, I think it may be 3 o'clock now that I think about it. So, so if you want to come here Tuesday or Thursday at 3 o'clock, meet in my office, and we'll find a room to go to. But if Birmingham is more convenient to you, check with Miss Martin, because she's meeting with another 1 or 2 students, and I don't remember what afternoon she's meeting. And then Miss DeRacy, who is the really going to be the coach, she, I think, said Monday and Wednesday afternoon were the most convenient for her. And she's going to be meeting with students sometime Monday, Wednesday afternoon on the Birmingham campus. So you got 3 possibilities, and then Dr. Thomas, I think, is available to meet with students too. I didn't hear her specify times. So I encourage you to give it a shot. You know, we probably are only going to meet until the first week in October. I won't be able to go to that first competition because I've got a nephew getting married in Dallas, Texas that weekend, so we'll be gone that weekend. So, but Dr. Thomas, I know will be going, and Mr. Racy, I think, will be going too. So it should be a lot of fun. So please consider it, and you get a whole bunch of free tutoring, you know, in calculus, because working those problems, they look like fun. There's no pressure at all. Nobody grades you or anything else. They just award the top 3 in every. It's the top 3 individuals and the top 3 teams. So yeah.
Is it competition at the school?
Yeah, it's within the state of Alabama mostly, and the 2-year colleges. Yeah, it's going to be at Shelton State in Tuscaloosa. The competition, I think that's the 9th of October or something like that. And so yeah, it's a competition, but it's fun. It's not cutthroat or anything else. It's just fun, you know. And I think you'll, frankly, just looking at that, it looks like you're going to learn a lot, so consider it. Please consider it. And if you are interested, either let me know or see Dr. Thomas. You know where our office is. Go down this half flight of stairs. The first classroom, you go past the restrooms and water fountain stuff. You go past the hallway that goes to students' financial services. Then keep on going. The first classroom on the right is 254. It's a big classroom, got 2 doors. Then there's 2 office doors right next to each other. And then the last classroom on the right is 256. Dr. Thomas is the office closest to 256. Ms. Duncan is the one closer to 254. Dr. Thomas is the one right next door to 256. They don't really have numbers. Someone put a sign up and called it 255A and B because it's in between 254 and 256. But this is 255, so that's just, but she's 255B if you go by that. So please consider it. It's I think you'll benefit from it, and I think you'll also enjoy it. So anyway, that's my advertisement. So let's get on. Okay. I just started talking about, this is where we left off last time was Chapter 6, Section 6.2, page 342, Example 3, right at the bottom of the page. And what the example said is compute the volume of a sphere of radius capital R. Okay. Now, some of you may know this right off the top, and all of you could look it up and find out what the volume of the sphere is. We're going to compute it. And I got to thinking that maybe one of the things I didn't do, because see, the book gives you the illustration, and it's pretty easy to follow that. But let's imagine they didn't. What are some things to do to draw these figures so you can set them up to compute? Well, the first thing to do is determine where is the best placement for your coordinate system, okay? And as you see here, and I think you would, as you think about it very much, putting the center of that sphere to be the origin would be the best choice to make, okay? Now this is 3-dimensional because this is a sphere. The ball comes out of the board and goes into the board. But still, they chose here, and this is fine, to do x-axis this way, y-axis this way. So that would mean the z-axis would be coming out of the board like this. But we're not going to fiddle with the z-axis on this problem because our symmetry takes care of everything there. In fact, symmetry will take care of a lot of things you'll see. Okay, so unfortunately, they already drew everything for you, okay? And you see this is a sphere, 3-dimensional. This is coming out of the board, that's going into the board. Let's pick anywhere between the origin and the limit r, that's going to be the radius. Anywhere along there, they chose an x. You could have chosen y. You could have done your circles this way. That would have been perfectly fine too. It doesn't matter. So they chose x, so we'll use x. And let's do a representative cross-section of that sphere right there at position x. X is somewhere between 0 and capital R. Well, that's the radius of the sphere. Okay? So for any x in between there, pick the value x, and then you'll see the cross-section that you get by taking a dx, a delta x, dx thickness here, cross-section of that, that gives you a circle. They did a little bit of dimension in it so you can see it's a circle. So the thickness of that is dx. The radius will be this thing right here. That's the thing you don't know, okay? That's the thing you need to compute. But you've already said this is x here, how far on the x-axis between 0 and r. And you know that this point up here, any radius of that sphere, no matter where you draw a radius of the sphere, that's going to be capital R because you put the origin in the center. Okay? So that means that's radius r. Well, then what's the radius, little r, of this circle here? They do little r because it's smaller than this big R. Big R is fixed in the whole problem. That's constant. Little r is a variable here. What's this radius here? Well, that's your y value, isn't it? And what do we know about that y value? because this is x, that's y, that's perpendicular there, right? So that means that x squared plus y squared is equal to capital R squared. This is your y, but that's also your little radius r. So x squared plus r squared is equal to capital R squared. Solve that for the unknown, which is your little r. And that would be r squared minus x squared. Take the square root of that. That would be little r squared. Take the square root of that. And that gives you your radius of this circle in terms of the radius of the sphere and the distance x. This then is what we're going to, and remember, the area of the circle times the thickness of the circle, that's going to be the volume of that little wedge, right? Area being pi r squared, but guess what? If you square that, you go back to being. So what you're doing, you're looking for the volume of the sphere, and the volume of the sphere. Okay, let me get my oh, here we go. This isn't quite the color I want, but as close as I can get. Okay. The volume of the sphere is going to be the summation of the volumes of all these wedges, or I'm going to call them circles, okay? You're doing the volume of all the circles this way. This is the representative of that circle. Its volume is going to be the area times the thickness. What's the area? Area of this circle right here. Okay, that's going to be pi. The area is pi little r squared. But little r is be pi times the square root of capital R squared minus x squared squared. And what's that going to be? What happens when you square a square root? That'll be pi times r squared, capital R squared minus x squared. So there's your area of that circular disc. We haven't started calling it this yet, but that's what it is. What's the thickness of it? dx, right? Because you chose your delta x's along the x-axis there. So your volume is going to be, now we'll change it from a summation to an integral, okay? And now that integral would be from minus r, I should have put the minus sign elsewhere, sorry about this. Okay, from minus, this thing is so aggravating. Okay, there's just not enough papers here to back it up good. I've got to hold it sometimes. From minus r to capital R of your area, pi r squared. So since pi is just a constant, we'll put pi on the outside. And this will be r squared minus x squared. That's your r squared, little r squared, times your thickness, dx. There's your summation. What's that? Okay. You're doing your x's from this negative r to that negative r to get all the slices of the pie, of the disc. They're all circular things. Right there, it's just really a point. There, it's a point. But everything else is circles getting bigger and then getting smaller again. And you're summing all those up. Now, do you see something being nice and lazy like you are that you can do to simplify this? Half of it. Be lazy. Okay, no reason to do any more work than you need to. So this is also pi, but you're going to double it, so it's going to be 2 pi times 0 to r. Just going from 0 to r, and then we're going to double that, because this half of the circle of the sphere is going to be the same as the other half, the volume, of r squared minus x squared dx. Okay, I think we can do that one, can't we? That would be 2 pi antiderivative of, now remember, capital R is a constant. It's just the radius of the sphere. So what's the antiderivative of capital R squared? R squared times x minus x cubed over 3. And we'll evaluate that from 0 to r. I already have our 2 out front, so that accounts for that. So this will be 2 pi times, when you plug in a capital R for x, what do you get? R cubed minus r cubed over 3. Well, I think I can figure out what that is. That's 2 pi times, what's r cubed minus a third r cubed? 2/3 r cubed. Right? Okay, now multiply, and that gives you 4/3 pi r cubed.
How did you get R cubed?
What's that?
How did you get R cubed?
This?
Yeah.
Okay, I cheated. I mean, I went by what he said. Theo told me to. That's how I did. No. Okay, this is 1 r cubed minus a third r cubed will give you 2/3 r cubed. Or, if you want to be more mathematical about it, get the least common denominator of 3, but r cubed is how many thirds of r cubed?
But how did you get the R cubed from the R squared?
Okay, yeah, oh, I see. Okay. You're plugging in for x. X is your variable here. That's your dx there. This is a constant. So you put r squared times r. That's r cubed. Yeah. And then put an r in for this x, and that would be r cubed over 3. Okay. I thought you were talking about this thing. Okay. And guess what? I think we all knew, didn't we? That the volume of a cube is, of a sphere is 4/3 pi r cubed. We knew that, didn't we? Yeah, of course we did. Okay, but even if we didn't, we could have looked in the front of the book, that not that very first page, but the next one. There is the sphere, the volume of the sphere. Now they have the radius being little r, 4/3 pi r cubed. Good for them. They got it right. Okay. Does that make sense? All right. Now the next thing they sort of throw in here, and it's a nice little principle. It makes you wonder, okay. It's called, I don't even know how to pronounce this, a good Italian name. Cavaleri's principle states that solids with equal cross-sectional areas have equal volumes. Let me blow this up a little bit. Solids with equal cross-sectional areas have equal volumes. Okay. And this is sort of the classic representation of that. If you had a stack of coins here, these must be Italian lira or something like that. I don't know what they are. Okay, they're obviously not our coinage because they're silver in the middle and gold, brass on the outside. And you have a stack of coins here. Yeah, the volume of that stack is pi r squared, where r is the radius of that coin, pi r squared times the height of that stack. Okay? Now, what if the stack was all wobbly or leaning or something like that, but it was still the stack of the same coins? Same volume, even if it isn't, because the cross-sectional area is the same of every coin, and the height is the same of the stack. So yeah, it has the same volume. There is actually, in New York City, I've only been to New York City once, but there's one building I found it just truly ugly, but some architect made it so it's wobbly looking and weird looking, but if I don't know this is fact, if every slice of that is the same area, then the building has the same volume as if you could build a nice, straight, perfectly tall building. Okay, if you had the same height. So they just sort of threw this in here. I'm not sure we use it anywhere. Maybe we do, but that's Cavaleria's principle. Which, by the way, gives you one potential paper topic, who in the world was he? Another one might be, how did he come up with this principle? Or another one might be, what were some practical applications of this, or maybe not so practical applications? How is this actually used in mathematics or architecture, engineering, or something like that? I don't know if you find any other topics you could, but I can think of at least three. I don't know if you can find enough material on them. I know you can on who he was and probably how he developed the theorem or principle. Practical applications, you might find some. I don't know. I'm guessing there are because they have a principle named after him. Okay. That's all they do on it. They don't give you any problems or anything else. So let's go on to the next topic, and this is density. Okay. Now, yeah. Being also a physicist, I really don't like their approach to this all that well, but it's fine, it's good. But here is a statement. Total mass is equal to a density times some other measure. Okay? Now that's a rather vague statement. Most of the time I would say total mass would be mass density times volume. Okay? When I say mass density, that's mass per unit volume. Okay? That would be a density. Multiply the total mass, multiply the density times the volume, you get mass. But what if the object or the thing that you have doesn't just have a volume density, it has an area density. Okay? Then it would be area mass density times area. But then if you go back another step, what if this is now a rod, and the rod has various density? Over here it's really dense. Out there it's not so dense. Then it has a linear mass density. Okay? Area mass density would be areas vary. Okay? And they wouldn't have to be all in one direction. It could be light density here, more dense here, and but it would be area mass density times area or linear mass density times length. Okay? And that's how you get total mass. That's just a generic statement. Or the volume mass, the total mass would be the volume mass density times the volume. That would also work. Okay? They're going to start with linear mass density. I'm not sure why, but they do. And what we mean by linear mass density is how much mass you have per unit length. So let's just imagine it was a rod of varying densities. Okay? Either this rod is made up of, say, a steel that is an alloy of several different materials, and this end has more iron in it, and this end has more chromium in it. So the mass density varies from that of iron to chromium along there. And there is some function that is your linear mass density. Well, what you do is a dx, okay, for the thing. You have the linear mass density according to the length, multiply that by the length, dx, and that gives you your total mass. Do your summation or your integration. Okay? So, I just gave you the quick and dirty of what they're doing a little more slowly on is this. So here you have a rod. The rod has length. It's going from x0 to x sub n. This is from A to B. So the length of that rod is B minus A. It could have been over here. This could have been the A here. That could have been the B here. It's B minus A. No matter which side of this, it could have all been over here. B minus A. It's always the farthest to the right minus the farthest to the left. Your assigned numbers will take care of that issue for you. Okay? So that's the length of the rod. But because it may have a density that depends on where you are along the rod. This could be far denser here and getting less dense as you go. It could be very low density here and getting denser as you go. Or it could be starting low, going dense, then getting less dense, going more dense. It's just varying with the displacement. This is some function of your displacement. Okay? Then what we do, we divide this rod into n equal pieces. So x of 1, x of 2, this is x of 0, x of 1, x of 2, x of 3, x of I minus 1, x of I, x of I plus 1, all the way up to x of n. Split it into n equal pieces. Then for any piece of that rod, it has a value somewhere between x minus x, I minus 1, and x of I. We'll just call it x of I, okay? If you get these small enough, it doesn't matter what you call it, okay? And somewhere in between that, x of I minus 1 and x of I is a point Ci, and we'll use that for its density, okay? P of Ci. And this will change depending on which piece of the rod you were talking about, okay? Then the mass of that wedge of the thing, split this into delta x's here. Delta x is x of I minus 1 minus x of I minus x of I minus 1. And we'll assume that if it's a small enough piece, the density isn't changing much. Okay, it is a function of distance, but if the distance is small, it's not changing dramatically. It's a continuous function. So it's not going to be plus 55 here and 0.01 here. It just can't do it that quickly. So for any given piece, it's going to have approximately the same density. So that's why they put approximately equal to the rho at C sub I times your delta x. That'll be the mass of this piece. Then you're going to sum all those together from x equals A to x equals B, and then you'll have the total mass of your thing. Which, if you take the delta x being small enough down to dx, then that's an integral. The total mass of the rod is equal to the area under the graph of the mass. Oh, and here's the graph of the mass. I thought they were just showing up. That's the graph. So it starts off low density. It gets greater and greater density till it maxes out somewhere about here, and then starts falling off in density till it's back about where it started there, with the largest density somewhere in between. It doesn't matter what the shape of that is, but you're integrating this rho of x times your dx, okay, from x equal A to x equal B. That gives you total mass of the rod by little sections, okay? Summation goes to an integration. So they left off the summation part and went straight to the integration part. The total mass, there was a summation of all your rho sub Ci when I was going from 1 to n, or 0 to n, times your delta x of I, okay? So this would be, when you integrate that, the integral from A to B, rho of x dx. There it is. Linear mass density times linear increment. That gives you mass, and sum all those masses together, you get the total mass. Does that kind of make sense? Just like we've done most of our integrations before. Riemann sums to an integral. Okay, let's do example 4. I don't know if example 4, no, it's not on here, I don't think. So let's just go back here and do it on this one. Find the total mass m, so what we're looking for is m, of a 2-meter rod okay, of linear mass density rho of x is equal to 1 plus 2 times, no, x times, sorry. I don't know if I've told you this or not. I'm left-handed, so I like to have the book over here, and then I can read better. But if I do that, then my computer is here, and then that blocks as I write. Because I'm left-handed, I block the view. So one of the students in my other class insisted I move it here, so that's why I get lost here. Let me find it again. There it is, where the linear mass density rho. And by the way, linear mass density is usually given the symbol rho. Area of mass density is given the symbol sigma. It looks sort of like a, kind of take this rho and flip it that way. It's a sigma. And then the volume mass density is, goodness, I think they use rho for that too. Any of you in physics, what do they use for volume mass density? I think it's rho, isn't it? But anyway, yeah. I wish they did. I wish they would have used different symbols, but it's okay. It's a linear mass density. And this is 1 plus okay, 1 plus x, and I get crossed up in my pen here, times 2, there it is, 2 minus x. Okay. And this will be kilograms per meter. They gave you the length of the rod in meters, so this linear mass density is in kilograms per meter. Mass per unit length. Okay. Where x is the distance from one end of the rod to the other. Okay, what happens when x is equal to 0? What is that end of the rod? X equals 0. Yeah. What would be your density there? Yeah. Plug in a 0. Okay. Not quite. 1 plus 0 times 2, that would be 0. So 1 plus 0 would be 1. So linear mass density on this end would be 1. How about on the other end? That's 2. The length of the rod is 2 meters. So what happens if you plug in 2 in there? It's 1 plus 2 times 0. 2 times 0 is 0. 1 plus 0 is 1 again. So at this end it's 1, at that end it's 1. Everywhere else, let's just pick halfway in there where it's 1. What would that be? 1 plus 1 times 2 minus 1 is 1. So that would also be 1. Okay. Is it 1 everywhere? No, I don't think so. Let's take it at, in fact, maybe a better way to do this would be this. In fact, I think this would be a better way. 1 plus 2x minus x squared. Okay. Right. All right. Now, let's say halfway into the rod. I mean, half a meter into the rod. Not halfway the rod, that would be 1. We already did that. So if it's 1 plus 1/2 times 2 minus 1/2, that would be 1 1/2, or 1.5. So that would be 0.5 times 1.5 would be 1. Say again? 1.25. Okay. Yeah, I'm sorry. So this would be 0.5 times 1.5 times 1.5 would be 6. Is that 6.5? Why can't I do this in my head? Okay. Yeah, I can't even write it now. Maybe you don't want me as a coach on the math team. Okay. It's 1 plus 0.5 times 2 minus 0.5 is 1.5. This is 1 plus, that would be 25.75. So that would be, yeah. Duh. Okay. That would be 1.75. Okay. So the density starts at 1, goes up to 1.75, and then goes back to 1. Then when x was 1.5, that would be 1 plus 1.5 times 2 minus 1.5 is 2.5. So that would also be 1.75. So it's low density, higher density, dropping down to low density, high density, low density. So that's, yeah, it's a variable density there. And you can use that formula. Actually, will work better when you do your calculations. Okay, why not? Okay, so what is the total mass of that? Well, let's draw the rod. Okay, this is x equals 0. This is x equal 2 meters. Okay, and the density varies as rho of x is equal to 1 minus 2x minus, no, 1 plus 2x minus x squared. Okay. Well, there's your formula. Let's plug it in. The total mass would be integral from 0 to 2 of, you could have either put this one in, or I think it's easier just to do that one. 1 plus 2x minus x squared dx. That's then your length increment. Okay? And this will be what? Antiderivative. Second? You may have said it, I couldn't hear. X, is that what you said? X plus x squared minus x cubed over 3. Evaluate that from 0 to 2. I'll do the 0 part, you do the 2 part. What does that give you? 2 plus 4 minus 8/3. I'll do the 0 part. 0. Okay. Okay. And this will be what? Okay. Yeah. Okay. This will be 6, which will be 18/3 minus 8/3 is 10/3. Perfect. Okay. That would be the total mass of that. What the units of it? Kilograms, because you had kilograms per meter is your density, meter is your increment, so that would be 10/3 of a kilogram. Okay. And that's exactly what they got. Good for them. Now, in some situations, here is a generalization here. Density is a function, rho, of x and y that depends not just on the density to the origin, but also on the coordinates x and y. The total mass density or population is then computed using double integration, a topic for multivariable calculus, which we'll do toward the end of this term. We're not doing it yet, but we'll get to it before the end of the term. No, wait, no. That's in Cal 3. Cal 3 is when you do multiple. So we'll get to that later. So what we're doing now is, in some situations, density is a function of distance to the origin, okay? Not of a linear density, okay? Density to the distance from the origin. For the study of urban populations, now this is typically kind of true. Now, it's kind of not true, but you can sort of model it this way, that the density varies as you go out from the center of the city. Quite often, the population is pretty congested right near. So when R is very small, you have pretty large population density. Then as you go out, you usually get to a region. Now, it may be if your city center is very industrial, you don't have many people living there, so then it might be very small in the center, okay? But then you go a little ways out, you get a pretty large population density. Those are the urban dwellers. Then you go on out and things spread out a little bit, but then you get in the suburbs and they get more dense again. So again, you have a population that varies by distance from the origin. Now, what that almost requires is you to have this town whose topography is uniform, okay? For instance, Atlanta would be a far better model of this than, say, Savannah, Georgia, or Mobile, because Mobile's right on the bay, so its population is restricted by the water. It doesn't have people living on the water, okay? So you couldn't do that one. Birmingham would be easier than Mobile, but Birmingham has the mountains too, so our population density. But Atlanta would be pretty uniform. Not exactly. The airport messes that up. People don't live in that big area of the airport. They can't, but they used to, but they don't anymore. So yeah, you have some variation, but it's not a bad model, okay? And we then talk about a radial density function that could be getting smaller, bigger as you go out. Now what you do, if you have that situation, you have blow this up. And I mean, really what you have is something that's really akin to polar coordinates. I mean, that's really what you're dealing with here, but they're not calling it that, okay? If your density varies as you go further from the center of the city, it could be very low density here. It may be very high density. It just varies, by city by city. Right now, Birmingham is getting more dense in here. People are moving back into town, and there's still a lot of people in the suburbs, but our population density is actually increasing in close. They're actually getting the first grocery store, big grocery store. Publix is building a grocery store somewhere near the center of downtown Birmingham. And they haven't had a grocery store there since probably back when we first moved here. There was a Sears shopping center somewhere near downtown. It closed, and I think they had a grocery store in it, but they have little local markets, but that's all. The Publix is moving back. It indicates that people are moving back downtown. Gas prices, other things are causing that. Okay, so dividing the circle of radius capital R, that's going to incorporate the entire city, into thin rings. Now, what we have to do now is talk about what is the width of this ring, okay? Because now we're talking about a density that is more of an area density, see? So you are going to be dealing with that. Well, let's think about this ring right here. Around the collar here, okay. Let's imagine we could take this and stretch it out. What would be the length of that rectangle? It's not quite a rectangle, but close to it. If you stretch that out, what would be its length? 2 pi r, the circumference of that circle, okay? And we're using Ri for the ith ring here. It could have been here, wherever, the ith ring. 2 pi times Ri, okay? Now, the thickness of that ring is basically on this, your dr, okay? So the area of this circular strip, you might call it, would be 2 pi r delta r, okay? So you divide the circle into of radius capital R into n thin rings, and each one of those has a delta R, which is that total length divided by n. You have 1, 2, 3, 4, 5, 6. You do R divided by 6. However you divide that, R divided by the number of rings, that would give you your delta R. So your delta R is R divided by n. So you could plug that. Well, you don't want to do that yet, but that's what your delta R is. Okay. So, do they give us a problem here, or are they just still setting it up? Yeah. So what then you're going to do is do the population within each of these strips. Okay? So your population density will vary from R equals 0 to R equals capital R. Okay? And that is your population density, which I bet you they're going to call rho as well. Okay? But it's going to be an area density. Multiply that by 2 pi R delta R. Let the delta R go to 0, and then it becomes a dr. So you have rho of R, 2 pi R dr. Pull out the 2 pi out front, and I think you've got your density formula. Okay, let's see what else. Yeah, here's a population within. Yuck. Okay, the population P within a radius capital R would be the 2 pi R, that's your circumference. dr would be the thickness of that, and rho R would be the area population density. Okay? No, I'm sorry. Yeah, the area population density. Because 2 pi R dr would be an area, and this would be population density per unit area. Okay? So, again, you would have to be given that in population density per unit area, and then you do this R, the little r goes from 0 to that's your integration. Does that make sense? Okay. Let's do the next example. I don't do any examples with that. Oh, wait, I'm sorry. Yes, they do. There's one. Example 5. I was looking on the wrong page. I don't think they have a figure for this, do they? No. They go right in the Poiseuille flow. All right, so let's do this. Computing total population. Population of a certain city has the radial density. They call this the radial density. Density as a function of the radius r. Radial density function of 15 times 1 plus r squared to the minus 1/2. By the way, that means just the thing in parentheses is to the minus 1/2. Now, that's an okay way to write it. Most of the time you would see that is 15 over 1, the square root of 1 plus r squared. But that's a really good way to write it if you're going to use your population density function, formula, the integral. Okay? And with that being your, let's see, r is the distance from city center in kilometers. Rho has units of thousands per square kilometer, so that's, even though they call it a radial density function, it's an area density function because it's 1,000 per square kilometer. How many people live in the ring between 10 and 30 kilometers from the city center? So we're not looking for the whole population of the city, those that live from 10 centimeters from the center to 30 centimeters from the center. What would that be then? So what would be our population P would then be what? 2 pi out front, integral from 10 to 30, because it's not 0 to 30 now, but 10 to 30, and this is a kilometer, and it's per square kilometer, so that works okay. R is in there, and then your row of R was this thing, the 15, so I'm going to take the 15 and pull it on the outside too, so that'll make 30 pi, okay? 30 pi 1 plus R squared to the minus 1/2 dr. And I'm almost going to eat my words here, because in this problem, I don't want it written like that. I want it written like this. And again, I'm going to put the 30 pi, and I'm going to backtrack on that too, but I'll let you know that in a minute. Integral from 10 to 30. I'm going to write this as r dr over 1 plus r squared to the 1/2. I'm going to leave the 1/2 in there, but put it down below. Okay. Why would I do that? Yeah, okay, it's a negative 1/2 moves it down there. But why do I want to write it like this? You don't have to, but I just find it easier to see. Because how am I going to do that integral? Substitution, I like it. What are you going to substitute? Second, let u equal 1 plus r squared. Yeah, 1 plus r squared. I don't need the parentheses there. Sorry about that. I got carried away. Okay, 1 plus r squared. Okay, what do we do next with substitution? Then du is equal to, a little louder, 2r dr. Write it as a differential, 2r dr. Okay. Now we don't have a 2r dr, we have an r dr. So what might we do? Divide both sides by 2. So you have du over 2 is equal to r dr. Okay? So let's go back and write our population is equal to 30 pi, okay, integral, let's not mess with it yet. Your numerator is going to be a du over 2, so let's divide this by 2, so this goes back to being 15. I'll have to pull that 2 on the outside. There's your du, that's your 2r dr, except you divide out by 2. And then what you have in the denominator? One plus r squared was u. Okay, so that would be u to the 1/2, right? So now I'm going to go back and write this as u to the minus 1/2. It was okay written that other way before, but this I can integrate better. Okay, all right. Now, one thing we haven't done that we need to do is change our limits. Or you can carry it all the way through and then plug back in. It's usually easier to change limits. These are our limits for R. What would be our limits for U? When R is 10, what is U? 101. Looks like some big numbers coming up here. 101. And when R is 30, what is your U? 901. I'm wondering if I want to do it this way. 901. Okay, let's see what happens. So this is going to be 15 pi. That sounds good, doesn't it? All right. And then what's our antiderivative? to the 1/2 times 2 over 1. I'm going to take this 2 back out here and make that 30 again. Boy, we've been back and forth on that, haven't we? Okay, and evaluate this from 101 to 901. I'm not sure this is going to come out to be such a pretty number, but guess what? You got calculators, don't you? Okay, so this is going to be 30 pi times the square root of 901 minus the square root of 101. Okay, that's not that hard to do, is it? Some of you don't have calculators, huh? Oh, okay. Oh, okay. You trust the book? What you get? What's that? They get the, yeah. Okay. What did you get? Did you actually punch it in? What you get? Okay. And this is in thousands, so 1881 thousands. And guess what that is? That's 1,881,000. So basically about 1.9 million people live in between 10 and 30 kilometers outside the city center. That's a good-sized city, okay? That's a pretty good-sized city, okay? And that would be total population. Good deal. Does that make sense? All right. Just had some messy numbers to evaluate, but they're just numbers. Use your calculators. See what they are. This is now something, and I don't know, all of you are in physics now or not? Yeah. And is that physics 1 or 2 or, 213? Okay. I'm trying to remember, I've taught it before, if you have fluid dynamics or in that or not, or is that 214? I just don't remember. I taught 201 this summer and 214 this summer. I don't remember doing this then, so I'm guessing that, but I don't. Okay. Anyway, here we have fluid flow. When fluid flows through a tube, the flow rate, Q, is the volume per unit time. Okay? Well, they're not showing Q anywhere on here, but that's the volume per unit time. Let me give you an example. What are your majors? Chemical engineering. Mechanical? Mechanical, okay? I know you two mechanicals, you'll be dealing with this. You'll probably be dealing more with rate of reaction rates, okay? As two materials at different temperatures and pressures and stuff will react differently, have different rates. Same type of principle. But for you two, wouldn't be at all surprised if you might not have a problem like this one. How much air is coming out of this vent? Well, they'll give you the flow rate as in cubic feet per minute. CFM. Very common way of measuring flow rate. Okay? It could be cubic meters per minute, you know, but in a lot of U.S. type stuff, they measure this in cubic feet per minute. That's what the fan is producing. And then you have to figure out the cubic feet, you know, the area of the ducting and stuff like that. Yours would be reaction rate, which is sort of imaginary ducting, you know, and stuff like that, determined by temperatures and pressures. So that's the type of thing we've got here. Okay. Now, So flow rate, Q, and I'll write this down because I think this is pretty important. The flow rate Q, well, if I write it down, I'll lose the magnification here. Okay, let's see. Yeah, the flow rate Q, and this will be in volume per unit time. Like I said, cubic feet per minute, cubic centimeters per hour, it could be any kind of volume per unit time. And what that's equal to is your cross-sectional area, called A, times a velocity, V. Okay? Now, does that make sense? Well, area would be an area measurement. This could be, say, cubic feet. Area would be square feet. So you would take the duct here, measured how many feet it is that way, how many feet that way, multiply that. That gives you the area of the duct. So that the area of the duct times velocity. Well, velocity is distance per unit time, right? Distance is moved, the fluid is moved out of that cross-sectional area. Distance times area would be a volume per unit time. Yeah, that makes sense. That would be, you just picture a volume of fluid air coming out of there in a certain length of time, cut it off, and that's so many cubic feet per minute. Take that volume, don't let it dissipate, run it through that size of thing, that's cubic feet per minute. How much air moves through there per minute? Okay? So there is area times velocity. Cross-sectional area times velocity. Okay? And they give it in cubic centimeters per minute. Fine. Now, that would be if we had a perfectly smooth box that is coming through and no friction. In reality, it doesn't happen. There's always friction, even with air going through a box. There's always friction along the wall. Always. It doesn't have to be a rough wall either. There's just friction because the wall is there. Okay? Now, in reality, fluid particles do not all travel at the same speed, velocity because of friction. However, for a slowly moving fluid, if you're measuring it in cubic centimeters per minute, yeah, that's going to move pretty slowly. You consider the flow as laminar, which means that the velocity depends only on the distance r from the center. Okay? Now, the difference between that and what we call turbulent flow is if the air is moving really rapidly and there is so much friction at the surface, let's say it's going through a tube, so much of it, then you get air going in eddy currents. So some places the air is actually going behind because this is going so fast this way that it can't keep up, so that you get eddy currents. Think of what happens behind the motorboat blade, the blade in the water. It's churning up water, and the water's going in all sorts of directions, okay? That's turbulent flow. We're going to try to do it laminar flow. Now, this would be this thing, column of fluid passing a point P in 1 unit volume of time in a cylinder whose volume is pi r squared V, okay? Pi r squared is the area of this times V, that's the volume. That's if all the fluid was able to move down the pipe at constant velocity. We know that doesn't happen. This would have to be an imaginary pipe for that to happen. If there's a real pipe there, it's not going to happen. Reality is it looks more like this, okay? That the fluid coming into this, it's slowed down up here, its maximum flow is going to be right in the center. Now, it seems like to me they should have taken this cone and turned it that way. That would have made more sense to me, but they turned it this way because they were looking at it from this end. Okay? This is called laminar flow. The velocity increases toward the center of the tube. And that's true, Have you ever really watched water come out of a hose? Okay, it doesn't just come out boom, you know, it comes out and you got sort of spiraling going around the outside, but the water right through the center is coming out fastest. Okay, you can take your finger and just move it a little bit there. You hardly change the flow at all. You get the thumb over the end of it, you know, you're really changing it then, because that's where it really was coming out the fastest. Just around the edges, you're hardly changing it at all, because there's already friction there. So this is what laminar flow looks like. I'll blow that up for now, but as soon as I write something on here, it's going to go back. So this is laminar flow. Not just the whole thing moving down, but it moves down in a parabolic shape. All right, so now approximate the rate of flow. Let's see what the next slide is. Yeah, this is helpful. Okay. Of course, I'm going to lose this as soon as I go to write something on it, but at least this is helpful for now. So this is your laminar flow, and again, I want to flip that around and do it that way, but they're doing it this way. Laminar flow, the fluid particles passing through a thin ring. This seems like our population density, kind of, doesn't it? Thin ring at a distance r sub I from the center of the tube. All travel at nearly the same velocity, v of ri. Okay? So that velocity changes is close to zero at the edge, and it's at the max in the middle, and it's varying everything in between those two values as you go out. Okay? Now, let's take this ring here of thickness delta r, and its radius is ri. So again, just like we did before, the length of this ring would be 2 pi ri times delta r. That would give you the area of that ring. Okay? And all the water in that ring, pretty much, as long as it's a thin ring, is going at about the same speed. That will be our V of Ri. Now the V of Ri varies from near zero at the edge to the maximum in the middle. So that V of Ri is a function of the distance from the center of the hose or the pipe, whatever you've got there. So in laminar flow, the fluid particles passing through the thin ring, the distance Ri from the center, all travel at nearly the same velocity, V of Ri. Okay. And I mean, it's fine to do this, but what I don't get is okay. To me, this looks like a length measurement here, and they've got it as a velocity measurement here, which is length per unit time. So what they're saying is all along this is one time period. Okay, and that time period almost no water or fluid is doing here because that's close to zero. The maximum is here, and this is something else. So it would have made more sense if they said, this particular picture is in one of your time intervals, whatever that is, 1 minute, 1 second, whatever that is, this is the flow in that 1 second. Then that makes more sense to call that V of Ri. Okay, but that's just a little picky point. Sorry, didn't mean to do that. Just was bothering me. Okay, now with that in mind, let me see what the next slide is. Yeah, I was afraid it was that. Then let's look at the total flow rate, Q of I. This is the coming out of there. So your Q of I that's of that ring, that would be the cross-sectional area, which is your 2 pi r(I) delta r, okay, times your velocity, and that's your v of ri, okay? So it would be that area times that velocity. All right. 2 pi r(I) delta r times v of ri. Okay, so v of ri is your velocity formula there. Now, your total flow through the whole thing would then be summing all those for your I going from, is it going from 0? No, they're letting it go from 1 to r. Okay. No, 1 to n, sorry. R would be, let me do it this way. It's easier. Okay. You got n divisions here. That's the part they didn't show. Okay. 1 to n. Break this up into n increments here, n rings around the collar here. Then that would be of all your q sub i's, which would then be 2 pi times the summation I equal 1 to n of r I v r of I delta r. I guess you call that delta r sub I too. Or they just leave it delta r. Okay. You could put in a subscript there, but they don't. Okay, let's just leave that out then. All right, well, guess what we're going to do? Going to change that from a summation to an integral. So your total flow rate, Q, would be the 2 pi times the integral from r equal, this is a little tricky here. You could do r equals 0 to capital R. That's how they do it. 0 to capital R. I would be real tempted to do R to 0, but it's okay. Okay. And then you'd have R V of R dr. Okay. R V of R dr. Okay. Now, very similar to what we had before when we had population here and radial population density here. I mean, they look identical. Okay. It all works out. So before I go any further, the French physicist, they say physician, and maybe he was, but I would have called him a physicist, he was a physician, I'm sorry, he was. Jean Poiseuille, okay? And you could use him, even though he's not a mathematician, he's a physician, he's a doctor, okay? But he discovered this law of laminar flow. Why would a doctor be interested in this? What laminar flow is he interested in? Blood flow. Assuming your arteries and your veins are cylindrical pattern, things, which is a pretty good assumption, then the blood flow through that, and this is exactly who did it. Beat the physicist, beat the mathematician, the doctor came up with this. Discovered the law of laminar flow that cardiologists use to study blood flow in humans. Poiseuille's law highlights the danger of cholesterol buildup in the blood vessels. The flow through a blood vessel of radius r is proportional to r to the fourth, so that if r is reduced by 1/2, the flow is reduced by a factor of 16. So if you have plaque buildup or cholesterol buildup on the inside walls of your artery, as that builds up, the flow goes down, and as that goes down, it really restricts. Now, sounds sort of maybe like a gross comparison, but we live in an old house, 1930s house, actually built in 29, I think. We just discovered, we always heard 30s. Our plumbing gives us problems periodically. In old houses, it does. And as stuff collects inside the pipes, you don't notice it collecting because the water is able to get on through until suddenly when it gets small enough, then all of a sudden it backs up. Okay, it was flowing fine last week and the week before. It was building up stuff, but when you finally get small enough that it doesn't flow through, then you notice it. Okay, so within the last few months, we've had to have Roto-Rooter come in. They charged us an arm and a leg, because we've got to find a cheaper place to do it than that. But my wife's all over me about, hey, and I say, okay, never mind. We won't go there. All right. But this is life-threatening when it's in arteries. Okay. So let's use, so here's your flow rate. Oh, there is the formula, and that's on the next slide. Here is your flow rate. This is Poiseuille's rule. What? Hit the wrong key. This is Poiseuille's rule. Okay. No, this is it. This is flow rate in general. Okay. The next we're going to do Poiseuille's rule. This is the one that says, notice the similarity between population density. Basically looks the same. Okay. Now, according to Poiseuille's law, the velocity of the flow, and I don't think we have a slide on this, so let me check. No, this is something different. Okay. The velocity of the blood flowing through a blood vessel of radius r centimeters is, here's your V of r, this is on Poiseuille's law, okay, is equal to K, some constant, times r squared minus little r squared, okay, where r is the distance from the center of the vessel, okay, distance from center, and capital R is the radius of that blood vessel. Okay, let's do a little timeout here. This isn't the biggest, but these are approaching the size of the larger blood vessels. Okay, there are a little bit larger, but I'm not going to show you down there in other parts. Okay, but let's just imagine that. But that's a big one. Guess what a lot of your blood vessels are? Have you heard the term capillaries? Capillary is thread-like, about the diameter. If I had any hair, I'd show it to you, about the diameter of the hair. That's where all the action's going on. That's where, you see, there's no oxygen being moved. There's no nutrient being moved out of that vein or even the artery that's underneath there. You can't see the arteries over there deeper. Okay? All the action is going on where the muscles are using it. Those are capillaries. Thread-like. So guess how small this capital R is? Tiny. Okay? You get build up around a very small thing and it will close up really, really quickly. Well, guess what's feeding your heart? Capillaries. Okay? You get a little bit, and this is why, I don't know, a guy in my older brother's class in high school, Frankie O'Quinn, was in a pretty bad car accident, broke his leg, okay, compound fracture, okay. He was young, he was doing well, until a blood clot that they didn't know had formed, I think it was his femur, near there, broke loose and flowed and went near his heart, clogged one of those capillaries, basically completely closed. He had a heart attack and died in his hospital bed. Sitting there talking, laughing, having a good time. You know, some of his friends would come by, and suddenly he couldn't breathe because of blood clot. And that's why a lot of times they'll give you, nowadays, this is many years ago, they'll give you blood thinners if you have a really serious, I think, compound fracture or real severe bruising and stuff. They will usually give you blood thinners to keep those clots from happening. Now, the downside of that, if you have internal bleeding, the blood thinners make that easier to do. So they are balancing a really thin line there, trying to keep you blood clots from going up and blocking one of the capillaries that's feeding your heart, but also trying to keep you from having internal bleeding. It is a lot more serious than most people probably realize when you have those kind of situations. Okay, sorry. Didn't mean to get off on that. Okay, but this is Poiseuille's law, okay, where R is the distance, okay, yeah. And these are all measured in centimeters, this distance and radius, okay. K is some constant. Calculate the flow rate Q, that's what we're looking for here, as a function of R, assuming that K is, and this is a fair assumption, 0.5, and the units are rather strange, centimeter seconds to the minus 1. In other words, the product of a centimeter times is per centimeter per second is really what you're talking about there. Per centimeter second. Yeah, strange. Okay. So the flow rate is 2 pi, the integral. They're just saying 0 to R. They're not giving you a dimension for R. Okay. Your K is 0.5. So let's pull that on the outside, and that's 1/2 of 2 is 1. So that's coming on the outside. R times, here's your plugging in your VR. This R is from here. Your VR is, you already pulled the K on the outside, R squared minus little r squared, dr. Okay? My R's are really looking ugly today. Okay, let's do this calculation. Pi, because we got rid of the 0.5 and the 2. Now, you might want to do this. This would be r squared minus r cubed. If that's helpful to you, write that. You know, all you do is distribute the r inside there. What's the antiderivative of that? R squared over 2, because the first r squared is a constant, and the other r integrates to be r squared over 2, minus r fourth over 4. So this will be pi times, and evaluate this from 0 to r, from the center to the outer limit of that, and this would be, this is what you're plugging in for your little r. So what would that be? R fourth over 2 minus, capital R fourth over 2, R fourth over 4. And this would be 2/4 is 1/2, so this would be pi times r fourth over 4. Okay?
How did you get rid of that 2?
I'm sorry?
How did you get rid of that 2? How did you take that 2 from the pi?
Right here, because your K that we put in here, you see V of R is K times that, K is 0.5. So I put that in for V of R, so 0.5 I took on the outside. This 0.5 times 2 is 1. I'm sorry, I skipped too many steps there. I just have a limited number. So this is written like that, which is another way you can write it as they do in the book, pi fourth r cubed, r fourth, sorry about that. Okay? And this will be cubic centimeters per minute, I think it is. Second, no, per second. Okay, per second. Cubic centimeters per second. Yeah, because it's centimeters per second. Centimeter second. All right, and this is where they came up with that, because this varies as the fourth degree of the radius of that thing. So for a vein or an artery about that size, okay, small, okay, but it's whatever radius that is in centimeters, which is pretty small. A centimeter is about the distance across your little fingernail. So the radius of one of these veins that look like a pretty good sized vein, that's still a very, very small number of centimeters. Okay? And then this is a big one. The small one is really tiny. Just a little bit of plaque in one of those babies is going to clog it up really, really quickly. Okay. Now, the next thing we're doing is average value. And I know y'all have taken enough tests. How do you take your average score on a test? Let's say we have 4 tests this term. How are you going to get your average? Add the 4 of them together and divide by 4, right? Yeah, that's how you're going to do it. That's what we mean by average value. So here's how you write it in one, let's see. I'll do it here. A1 plus, how are we doing on time? It's what? Are we already past time? Oh, shucks. Huh? It's 11:07? Okay, we got 3 minutes. I doubt if we're going to have time to do average value, so we'll begin with average value next time. But I think I can give you some homework exercises, can't I? Okay. Let's do any of the odds 1 through 7. Any of the odds 9 through 13. Any of the odds 15 through 37, any of the odds 39 to 47. No. Stop at 37. We'll pick up the rest of them next time. Now, I gave 2 of you your test. You didn't come by, did you? So let me see if I can find that. I hope I put it in the stack. That looks like it's there, but let me, nope. Ah, here we go. Now, can I see one of yours? I want to make sure I'm getting in the same one. I will have several versions of this. That was yours. Yeah, both of you got it. Good deal. Okay, those are due technically a week from today. If you need more time, you can have it. But try to work on it. That gives you at least Wednesday. You can ask me questions. You can ask me questions today if you got it. Give you a weekend to work on it. But if you need more time, you can have that too. Just try to have it turned in before I give you the next test, which will be at the end of chapter 6. Okay? Good deal. All right, that probably ate most of my 2 minutes up, didn't it?